Let's look at a few more examples of related rates problems. These ones might be a little bit simpler, I think, than the latter problem, so I think they'll be a little bit more approachable if you felt overwhelmed in the last video. So the first example we'll look at, suppose that we have a point that's moving along the graph of y cubed equals x squared. When the point is at negative 8, 4, its y coordinate is changing by 2 units per second. How fast is the x coordinate changing? So this one I think is a lot more approachable. It's a little bit hard to draw a picture. You could graph this function. You might need to use a program like Desmos, or you might need to use a graphing calculator. You'd have x to the 2/3, which I believe would look something like this. Oops, it'd look something like this. But I don't necessarily need to even know what the graph looks like for this example because they gave me the equation. They said, all right, we're working with y cubed equals x squared. So they gave me the equation that relates x and y. They even gave me some other information. They gave me the point, which here, even though I don't have a graph or a picture like I did in the last example, I would still organize this information. I would say, okay, x, that's equal to negative 8. Y, that's equal to 4. Let's see, what else do we know? Its y coordinate is changing by 2 feet per second. So a few things jump out at me. First is the word changing. Anytime we think about change, I want you to be thinking about the derivative. And then the other thing I see is this rate right here, 2 units per second. Anytime you see a rate like this, 2 units per second, there we're talking about the derivative. So we're talking about the derivative of its y coordinate. So that means dy over dt, or y prime. It says 2 units per second. It doesn't say whether it's positive or negative here. In this case, we'll just have to assume that it's positive. We would like to know how fast is this x coordinate changing. So at the end of this problem, we want to be able to say what is dx over dt. What does that look like? So here, again, I've organized my information. Even though I don't have that picture, I think this is going to be incredibly helpful for us once we find our derivative. So let's go find our derivative. I'm going to take the derivative of this function with respect to time. So I want to take the derivative with respect to t. So I need to use implicit differentiation here. Derivative of y cubed, that's going to be 3y squared times either y prime or dy over dt, equals, on the right-hand side, derivative of x squared, that's going to be 2x, times the derivative of x with respect to time, so either x prime or dx over dt. So here's my derivative. I found my derivative. Let's take everything that we know and plug it into that derivative. So let's see. Oops, let's erase this so we don't mix it up for a negative. 3 times y, what is y? That's 4 squared. Times dy over dt, that's 2, equals 2 times x is negative 8, times dx over dt. So I should have this equation which I can solve for dx over dt. So let's see, this is 3 times 16 times 2 is equal to negative 16 dx over dt. Let me just check my math on that left-hand side again. Don't want to make a silly mistake. I've got 96 equals negative 16 dx over dt. So dividing by 16, I should have a negative 6 equals dx over dt. So dx over dt is equal to negative 6. Here in this case is really not a great way for me to check the sign. I just have to assume that it's going to be negative. I suppose if you looked at the graph, you could sort of intuit what the rate of change of x is, but I think that's a little bit more complicated than what we need to be doing. I would like to see a unit on your answer, though. So the rate of change in y is given by units per second. Units of x, I don't have one, I'll just say units. And then per second, that's our unit of time, so -6 units per second. Here is my answer. There is my derivative of x with respect to time.